Good morning. Let's talk about the position aspect of GD&T. There's a certification exam that you can take to establish your competency in GD&T. And I like to remind students that 30% of that exam is your competency on the position tolerance. And 30% of that exam is your competency on the other 13 types of GD&T callouts. So position is one of the most important aspects of GD&T. Here we're going to take a look at how things would work under a traditional dimensioning scheme. In this traditional dimensioning scheme, we have a hole with a plus minus value. Its center is located 2 from the left side and 2 from the bottom. So if we allow that 2 side to side and the 2 up and down to vary within plus or minus 5 thousandths, we have a 10 thousandths variation side to side and 10 thousandths variation up and down. This gives us the distance across the diagonal of this rectangle of plus or minus 0.007 or 14 thousandths across the diagonal. So this is a pretty traditional plus minus dimensioning system for locating the hole. What happens though is that we want to think about, in context of this hole, we're allowing a variation to the left-hand side of 5 thousandths, straight down of 5 thousandths. But if we come down a little bit, we end up being further away from the center. But if this distance away from the center is a perfectly acceptable part, is there a reason why we can't be that same distance away from the center, but straight out to the side? We can come all the way out here of 7 thousandths, right? Why can't I be 7 thousandths away from the center in any location and still have that be a functioning part? So this is the question we have to ask ourselves. An alternate version of this question is 5 thousandths really the farthest you can go and still have a functioning part? So if that's really how far you can be from the center, maybe a part made out here in the corner is a bad part and shouldn't be shipped, but right now it's passing. So in that case, maybe this distance of 5 thousandths from the center should be a circle itself and reduce the number of poor parts that are getting shipped. So when we call out a position tolerance, the position tolerance is the circle with a crosshair. We use a diameter symbol. So instead of identifying a plus minus system relative to a true position or the center point, we establish a circle going around there with which the center line of your hole must fall. These circle locations of position tolerance are typically located relative to 2 or more datums. The first one is almost always the bottom of the part or the back edge of the part. And that's going to establish the perpendicularity of the cylinder. When we call out position of a hole, we're not really saying the diameter is a circle, but really the diameter is a cylinder. So it's a cylinder with that diameter of 0.014, this circle here. But ultimately, it's a full cylinder where that axis can fall. So the first call out in the feature control frame, that letter A, that establishes our perpendicularity of the cylinder. All of our acceptable parts must have axes that fall within this slash line cylinder here. So that can be it's sliding down or coming up high, or it could be kind of at an angle. It could be out of perpendicularity within that same circle. By increasing from this rectangle or square shape to the cylinder shape, we increase the acceptable parts by 57%. So it's really used significantly to identify locations. When we switch to the positioning system, we use basic dimensions to identify where that center true position theoretically should be. So the square around the 2 means that the 2 no longer has a plus minus associated with it, that all of the variation establishments come directly from the feature control frame. When I go back to my feature control frame and I look at the precedence of the datums, the back of the part's usually the first one that establishes perpendicularity. And then we've got the basic dimension 2, that's measured off of the bottom of the part, B, and the basic dimension 2, which is measured off of the left side part, which is C. This does have a maximum material condition associated with it, and that is quite common when we're dealing with position. So position controls location, but also orientation, meaning that perpendicularity. And as I mentioned, it's very frequently used. It really contributes significantly to how the part functions, and making sure we've got some part interchangeability. Your theoretical tolerance zone is located at the true position, so that's identified by those basic dimensions. And we're going to talk about this virtual condition boundary for the max material condition or least material condition. We'll get back to that shortly. Here we're talking about an external feature, a peg. You can see that we've got a plate down here with a post coming up off of it that we are trying to inspect. The peg is established to have a diameter of 1 to 1.02, and the location of that peg has to fall within a diameter of 0.005 at max material condition relative to A, B, and C, which are not shown here. So for an external feature, the maximum material condition is the largest value. The actual mating envelope is established by this actual physical size. So the actual physical size of this object is 1.010 at this location. It might even be 1.010 here, up at the top. The actual physical size does fall within the size variation requirements. So the actual mating envelope is the size of the hole that this peg would be able to fit through. So the size of the hole that this peg would be able to fit through is 1.012. This is physically off of this single specimen. So with a max material condition of 1.020 and minus that actual size of the peg, we end up with a bonus tolerance of 8 thousandths. There is a geometric tolerance given of 5 thousandths, which means we have a total positional tolerance of 13 thousandths. That's a diameter, so it's going to be plus or minus 6.5, kind of all the way around from the center. So here's the virtual condition. This is the important idea. The virtual condition is the hole with which that peg will always fit through. So the virtual condition is your max material condition of the external feature plus the diameter of the geometric tolerance. So 1.02, the maximum material condition, because it's an external feature, we're going to get larger, so 0.005. So this peg will always, always, always fit through a hole that is 1.025 in diameter. And that's what the gauge is built to. The gauge is built to that virtual condition, max material condition plus the geometric tolerance, which gives us that 6.5 thousandths on each side that this could vary as its center location moves within that 13 thousandths diameter. So that's calculating the virtual condition of an external feature of a peg. So the virtual condition of an internal feature goes the other way. The virtual condition of a hole is going to be the maximum material condition minus the tolerance. So here for the center hole, we've got a diameter of 1.005 to 1.030. The max material condition of the hole is the smaller number. It's when the part weighs the most. So 1.005. And then for the position, we're going to subtract the geometric tolerance. So So 1.005 minus 0.060, and that's 0.945. That's the virtual condition of the hole, and that's describing the external feature or peg that would always, no matter what, fit through that hole when it's passing inspection. So we also have down here a hole, right? We've got 0.760 to 0.790. The max material condition is the smaller value. We subtract the geometric tolerance, and we're left with 0.750 is the peg that could always fit through that hole. You'll notice up at the top here that we do get some composite tolerances. And what that means is that the location of the center hole can vary more than the perpendicularity of that hole can vary. And we would check that with two separate gauges. The position gauge would have that peg of the 0.945 diameter, and it would also pick up the other datum references in the feature control frame. So it would be relative to the back face, it would be measured 2.5 up relative to the bottom face, and 3.5 over relative to the left face. So at that theoretical position of 0.25 up and 3.5 over, there would be a 0.945 diameter pin that this plate would have to fit over. For perpendicularity, the only reference is the back face. So this gauge is just going to be a smaller flat face with a peg. And that peg is also going to be the max material condition minus the tolerance. So 1.005 minus 0.005. So you'd have a 1-inch diameter peg just associated with the bottom face to verify whether you've passed perpendicularity. So 1 inch to check perpendicularity, 0.945 inches to check the location. We have more variation that's allowable on the position versus the perpendicularity. If these small holes were measured at 0.777, right, the bonus tolerance would be the difference between the actual measured mating envelope and the max material condition. So they have 17 thousandths of bonus tolerance. So the total position tolerance would be the 10 that's given plus the bonus tolerance. Another way you can think of this is the difference between actual, so actual is 0.777, and the virtual condition, right? And we said that the virtual condition was 0.750. That's the peg that'll always fit through it. So the difference between that virtual condition of 0.750 and the actual 0.777 is 27 thousandths. So that's the total tolerance available between that hole and the virtual condition. We always want to think of how we're going to inspect these things, and we would do that with a gauge. We want to make sure that the disc meets rule number 1, which is that it's the right size. So the large diameter is going to be between, 4 and 4.02. If it's too big, we have to scrap it. If it's too small, we have to scrap it. The first thing you check is the diameter of that large disc. Then we check and make sure that the holes meet that. So 0.510 to 0.540, as long as the holes fall within that range, that gets them past the first step of inspection. Then we confirm that the disc is perpendicular to A. So to confirm that the disc is perpendicular to A, we've got this gauge here, the outer ring. We do have max material condition. It is an external feature. So we're going to use the larger value, the 4.02, add on the geometric tolerance of the 0.010. We find the total variation allowed, or the virtual condition of the large disc is 4.03. So the disc has to fall within this opening of 4.03 without the pins inside here, but just the outer ring to fall within the perpendicularity variation allowed. So if it's running a little bit smaller, if it's 4, it can be further away from perpendicular. It can kind of tilt a little bit more side to side if it's smaller because it has more bonus tolerance within the gauge to inspect it. Then we're going to check the location of the holes. When we're creating a virtual condition for an internal feature, such as a hole, we take the max material condition, which is 0.510, and we subtract the geometric tolerance of 0.010. So we're going to end up with a virtual condition of 0.5 for the holes. That is represented here with the 4x.50. So the pins to inspect this represent the virtual condition. And what that means is when we get larger, we run up closer to the 0.540, we still have a pin of 1/2 inch, 0.5. So you got more variation that can slide around and still fit over that pin. That variation can be location. It could slide up or sideways or down, but it could also be perpendicularity. So that hole could kind of be tilted a little bit more and still fit over it if it's burning larger. The max material condition on B is appropriate because B is the outside of the disc, and that's a feature of size. We can only have max material condition on datums when we have features of size. It doesn't work for A, that's just a plane. Okay. And that means that as the disc runs smaller, or runs away from max material condition, gets smaller, closer to 4, the disc itself can shift more in its gauge, and that also gives you more tolerance on where those holes can fit over those pads. This is a lot simpler to inspect than if any of these max material condition callouts were left out. Next time we'll pick up with tolerances of 0, and least material condition, and some other aspects of position.